In this second video, we're going to review a little bit about mass spectrometry. I think it's likely that NMR was reviewed pretty well in Organic Chemistry 1, and please feel free to look through those notes and use the tables provided on Blackboard. It's likely that mass spec might be a little less clear to you, so let's talk about that a little bit. So first of all, what are the mass spectra we'll be using this semester? The mass spectra we'll be using are from an instrument called a GC-MS. GC stands for gas chromatography. It basically uses the volatility of various compounds to separate them. So, for example, it separates them based on boiling point. Now that is followed up by mass spectrometry. A mass spectrometer is this really intense instrument that can measure mass of very small things. It can help us determine the molecular formula of the thing we're looking at. Or in our case, it'll confirm the identity of our product. So let's talk a little bit about the instrument itself. So to begin with, you have your sample. You probably dissolve your sample in some type of solvent. That sample is injected into the instrument. It travels down a column where it is separated based on boiling point, and along the way is vaporized. That vapor is injected into the instrument. Then, once the sample enters the mass spectrometer, it is bombarded with a high energy electron beam. This gives your molecules charge. It also, because it's so high energy, tends to break some of the bonds in the compound. Next, you have these charged ions. They're accelerated through a series of magnets, and they're separated as they travel down this tube based on mass. So molecules with different mass will kind of be separated and analyzed on their own. Then eventually those ions hit some kind of collector, they are measured, and we end up with this beautiful mass spectrum that comes out of the mass analyzer. It tells us how much stuff of different masses there are. As we're looking at mass spectra, we'll be trying to identify some important peaks. We'll probably be looking at the peak of the entire compound with its full molecular mass. And then oftentimes we'll be looking at peaks of various parts of the compound where the bonds have broken. So how can we start to understand these mass spectra? Well, first let's understand how the ions are formed, because only ions can be detected. So the electron beam bombards the sample. This is like a super high energy electron beam, right? 6,400 kilojoules. It only takes 400 to cleave a sigma bond, so this is more than enough energy. Generally, what happens is that a radical cation is formed. So your molecule loses an electron, becomes positively charged. We call this ion the molecular ion or the parent ion. It will generally have the same mass as the molecule you're working with. And this is kind of how we can understand it. So we have the molecule hit by some electrons, we make this radical cation. That breaks into pieces, and the mass analyzer can analyze any cation, including fragments or the molecular parent ion. What types of fragmentation should we look for, and how do we know what the fragments are? Well, folks, we have to do a little bit of math here, okay? Generally, single bonds are broken. These ones are easier to break. right? Breaking a single bond should be easier than a double or a triple bond. So these ones are most often broken. And an example of kind of a very simple mass spectrum is given below. For example, let's say you have a spectrum, you see masses of 16, 15, 14, etc. We know the molecule we're working with is CH4. We got some methane. We should be able to identify that the molecule with a mass of 16 is the parent or molecular ion. Mass of 15 has lost 1 hydrogen. Mass of 14 has lost 2, etc. The molecules we will be working with are a little bit more complicated. So let's talk about some of the types of fragmentation we can expect. The most common type of fragmentation that we're going to see is alpha cleavage of carbonyl groups. So here's your carbonyl group, right? The most common bond to break will be the bond on either side of that carbonyl. When those are cleaved, you'll get something that looks like this, some resonance stabilized ion, plus the thing that broke off. So really all you have to be able to measure is like, what is the mass of the thing that broke off, and do I see that mass on the spectrum? And what is the mass of the other thing, and do I see that mass on the spectrum? One particular case study that we should be used to is the fragmentation pattern of carboxylic acid derivatives. They undergo alpha cleavage. However, for a carboxylic acid, for example, super easy to lose that hydroxyl. Super common. What's less common is loss of the alkyl chain, okay? So we're talking about cleavage of this bond for the carboxylic acid derivative is more likely than cleavage of the alkyl bond, okay? So one breakage is easier than the other breakage. And so something that we might expect to see in class is shown here. Let's say we're looking at a product that has a molecular weight of 88. Let's look at some peaks. Well, here on the spectrum, there's going to be a smaller parent ion. In many of the mass spectra that we will look at, it'll be a little bit bigger than this. You can also see, there's something with a mass of 71, right? Take the difference in mass and let that help you figure out what has been lost. In this case, it's looking to me like the difference in mass, if I do some quick mental math, is 17. Well, if we add the molecular weight of oxygen with hydrogen, I think that's 17. So these are the types of math that we have to do. Now additionally, right, this is less common, but it looks like we had a cleavage of the alkyl chain because we have a fragment at 60 and a fragment at 45. So less common, but possible. And so we just need to be able to kind of think through some of these different types of cleavages. This one in particular, I'll focus much less on because you can see there's also a bit of a rearrangement of atoms. We're going to focus less on rearrangement and more just being able to recognize, the more obvious chunks that can break off. Now, the other type of cleavage that is most common besides alpha cleavage is just inductive cleavage. This is cleavage of almost any other type, right? So let's say we're starting with this molecule here on the right. Inductive cleavage could be if, this methylene group breaks off. Or inductive cleavage can be when this kind of propyl group breaks off. We should be able to kind of guesstimate what's what based on mass. 15 is pretty clear, 12 plus 3, a carbon and 3 hydrogens. We'll get used to this as we go along. And so folks, keep all of these things in mind when you're looking through the mass spectra. Keep in mind the parent ion and try to, get kind of comfortable thinking of groups that might break off. What's the mass of an OH? What's the mass of a CH3? Some of the things that we'll have to work on together for the rest of the semester. And this wraps up the video about mass spec.